In this video lesson, we're now going to look at acceleration quantitatively, or in other words, we're going to use math in order to figure out some information about an object that's in motion. So first, let's look at a graphical approach. The situation is this. A cart starts with an initial velocity of 4 meters per second, and it has a uniform acceleration of 2 meters per second squared for 5 seconds. And we're going to assume that the object starts from the origin. All right, first thing I want to point out is this word uniform. Make sure you understand that uniform means constant. So this object is speeding up with a constant acceleration of 2 meters per second squared. What we're going to do is we're going to go ahead and make the graphs first quantitatively, and then we're going to answer some questions on how we can figure out some information. All right, so what are some things that the problem tells me? Well, first of all, I know it has an initial velocity of 4 meters per second, and it's accelerating with a positive 2 meters per second squared. What that means is that it's speeding up, since velocity and acceleration both have the same sign. What I'm going to do now is I'm going to go ahead and make the graphs. Now, in this situation, I'm going to actually start backwards, and I'm going to start with the acceleration graph, since I know my acceleration is the 2 meters per second squared. So it tells me for 5 seconds that the object is accelerating with a constant 2 meters per second squared. What that means is that it's going to be a straight horizontal line for 5 seconds at the 2 meters per second squared mark. Now, if you remember the information from the previous video, we know that the area underneath an acceleration graph will tell us delta V. So in other words, the area under this curve right here, namely the area of a rectangle, that's going to tell us what the change in velocity is. So if I take the area of that rectangle, I get the base, which is 5 seconds, times the height, which is 2 meters per second squared. After I reduce the variables down, I end up getting that 10 meters per second is the delta V. Now notice, it's the delta V, or change in velocity. That doesn't mean it's the final velocity, just how much the velocity was changing. Now that I know that information, I can go over to my velocity graph. First of all, I notice that the initial velocity was 4 meters per second. Or in other words, when time was 0, the velocity was already 4 meters per second. So I'm going to, on my velocity graph, mark that by putting a dot right here at 0, 4. At time 0, it was 4 meters per second. Now, I know from my previous graph, the one that I just drew for acceleration, that my velocity changes by 10 meters per second in 5 seconds. So in 5 seconds, I now should be 10 meters per second greater. Well, if I started at 4, that means that at 5 seconds, I'm now going 14 meters per second, or a delta V of 10 meters per second. So now I can make this graph by just connecting those two dots. So notice I have my velocity graph now, quantitatively accurate, going from 4 meters per second originally, now to 14 meters per second in 5 seconds. Finally, I want to draw my position versus time graph. Well, let's think about this. We know that the object is starting at the origin because it tells us that we can assume that. And I know that the object is moving away from the origin, speeding up. So that tells me that the object is going to have a position versus time graph that looks something like this. Now, we just need to figure out what is that quantitative value. Or in other words, at time 5 seconds, where is the object? How far had it gone away from the origin? So we can solve that looking at our velocity graph. Remember, the acceleration graph's area told us the change in velocity. If we take the area under a velocity graph, that's going to tell us change in position. So let's figure that out. Now, if you look, the area underneath this curve is rather irregular. Or in other words, it's a shape that maybe we're not used to. The area, or the shape, is a trapezoid. Now, if you know the area of a trapezoid, you can use that. But let's say you didn't know the area of a trapezoid. That's no problem. What we can do is we can break it up into some simpler shapes by doing this. So this would be the area of the triangle, and then this down here would be the area of the rectangle, and then we would just add them together. So let's do those. First, I'm going to go ahead and do the rectangle. The rectangle is just base times height. The base is 5 seconds, and the height is 4 meters per second. When I multiply those, I get 20, and the seconds cancels out completely, so 20 meters would represent the rectangle. Now I have to do the same thing, but for the triangle now. The triangle is 1/2 base times height. 1/2 of the base is 5 seconds. And what is the height? Notice the height of the triangle is just right here, or in other words, the change in velocity. And we've already calculated that out to be 10 meters per second. If I multiply all those numbers through, I end up getting 25 as the number, the seconds would cancel out, and meters is my overall unit. So the area of the triangle is 25 meters, and the area of the rectangle is 20 meters. So that means my total delta x is 45 meters. Now remember, that's just delta x, or how the position changed. But remember, our object, we assumed, started at the origin. So if the object started at the origin, which is 0, and the position changed by 45 meters, that means that my final position on the y-axis must be 45 meters. Now, what if the object did not start at the origin, but what if the object started at the 10-meter mark? How would the graph look different? Well, all that means is that our graph would start somewhere up here at 10 meters. Our shape would still be the same, but that just means at 5 seconds now, I wouldn't be at 45 meters, but I would be at 55 meters. Now, that was a graphical approach. What we're now going to go through is we're going to go through kinematic equations. These are equations that accomplish the exact same thing, but they do it in a different way. They do it in equation form. The equations are going to come from the graphs, and we're going to show examples of that. These equations are dealing with motion that has uniform acceleration. So be careful. You have to make sure that you only use these equations which are dealing with constant acceleration. And lucky for us, in Unit 3, everything is in constant acceleration. Now, since these are equations where units are going to be canceling out, make sure that your units are in the proper form. So velocity is going to be in units of meters per second, time will be in seconds, and acceleration will be in meters per second squared. Now, what if you were given a velocity in miles per hour? Does that mean you need to convert your units? Well, maybe, but if your time is in hours and your acceleration is in miles per hour squared, you could leave your units like that, because notice that all the variables would cancel each other out. They're all matching each other. But let's take, for example, your velocity was maybe in meters per second, but your time was in minutes. That you would require some converting. You'd have to convert your minutes into seconds before you could use these equations. Okay, now that we know the general rules, let's look at the first equation. Kinematic equation number 1 is going to deal with a velocity graph. Alright, if you're looking at this velocity graph, you can see that the velocity graph is a line, and that has the general form of y equals mx plus b. Now in physics, we never leave anything in general equations, but we rewrite them to be equations that match physics values. So in this problem right here, what would the y be in? Well, the y-axis is velocity, so my y is going to be v now. Now, m is slope. What does the slope of a velocity versus time graph tell you? If you remember from the last video, the slope of a velocity versus time graph is acceleration. And so my m, or slope, would be a. The x value, or x label, is time. So that would be t. And then finally, plus the y-intercept b. Let's think about it. What does the y-intercept of a velocity versus time graph tell you? Well, what it tells you is when time is 0, it tells you what the initial velocity would be. So my y-intercept would be initial velocity. Now initial velocity can either be written vi, or you may sometimes see it written as v, what we call v naught, or v sub 0. They're both the same thing. Now if this is initial velocity, what would this velocity be? And the answer would be v final. So our first kinematic equation is this. V final equals AT plus V initial. This is kinematic equation number 1 out of 3. So let's look at a sample problem. Alright, what I'd like you to do is pause the video and use this first kinematic equation to solve this problem. Okay, go ahead and check your answers with what's on the screen. First thing to notice is I'm using this first kinematic equation right here. The second thing is notice how I've substituted the values in. My final velocity was 23. I was solving for acceleration. My time was 4.5 seconds. And notice my initial velocity was 0. I can assume that because the problem tells me that I'm starting from rest, which means 0 meters per second. Once you isolate acceleration using your algebra skills, you would get the answer as 5.11 meters per second squared. All right, this is kinematic equation number 2. Kinematic equation number 2 comes from a rather complex system of equations problem. So I'm just giving you the equation here. So notice what it says. It says V final squared equals V initial squared plus 2 times the acceleration times delta x, which remember, delta x is your displacement, or how far the object moved or changed position. So let's go ahead and use this kinematic equation to solve for our second one. Be sure to write this equation down before allowing the video to advance to the next slide. Okay, just like last time, I want you to pause the video and use kinematic equation number 2 to solve this problem. Okay, you'll notice on this screen right now that I don't have the final answer yet. I've just included the work. So notice that kinematic equation number 2 is written right here. Then I substituted the values. My final value, or excuse me, my final velocity is 25 meters per second. Notice it gets squared, is equal to my initial velocity, which is what I'm solving for, squared, plus 2 times the acceleration times the displacement or change in position, which is 45 meters. Now below that, I've got it simplified out. 25 squared becomes 625 equals the initial squared is still what I'm solving for, minus negative 315 is what I get when I multiply these three values together. So now I've got it finally figured out to be 940 equals V initial squared. It's important to note that this is probably one of the most commonly missed steps by students. They get to this point and think 940 is the answer, but you can't forget to square root the answer. So V initial, after I square root 940, ends up being approximately 30.66 meters per second squared. Or excuse me, meters per second. The last kinematic equation is going to come from something like this. So on the screen, you notice that we have another velocity graph. Notice what we know about it. Well, first of all, we notice that the velocity is a positive slope, meaning my acceleration is positive. It's moving away from the origin because it's drawn in the positive region. But also notice that it does have an initial velocity, which a lot of times that does happen. So the last time we looked at a velocity graph, we wrote an equation that looked like the slope of the line. Now what we're going to do is we're going to look at not the slope, but we're going to look at what would the equation look like if we wanted to take the area underneath this curve. Well, at the beginning of the video, we did something like this. Let's recall what we did. Remember, we broke this shape up into two simpler shapes, a rectangle and a triangle. And what did the area underneath of a velocity graph tell us? The area underneath a velocity graph is telling you the change in position. So we're going to go ahead and write an equation that would be to help us find the change in position for this object. So delta x equals the area of our two shapes. In other words, the area of the rectangle, base times height, plus the area of the triangle, 1/2 base times height. Now, let's plug those values in because we need to make sure that our values are actually physics values and not general values. So delta x would still be delta x equals. What does the base represent in the rectangle? Well, the base is the time. Now, what does the height represent in the rectangle? Notice the height represents whatever the initial velocity was. If the initial velocity was up here, then that would be the height. It's whatever the initial velocity value is. So the area of our rectangle ends up being just the initial velocity, which is the height, times time, which is the base. Okay, notice I rewrote that and flipped it around, but it's still the same thing. Plus, now we have to write the area of the triangle. Well, we have 1/2. What's the base of the triangle? Well, that would be time. And what would be the height? Well, the height would be whatever the final velocity was minus the initial velocity. Or another way of writing that is delta v. Now, we have our kinematic equation written, but the problem is we have it written in such a way where there's not acceleration. There is no a value in this formula. But recall that acceleration is just change in velocity over change in time. What if I rewrote that equation? Notice right here, this is the same exact equation as I had up here, only now instead of solving in terms of A, it's now solving for delta V. Since delta V equals acceleration times time, I'm going to take that and plug that in for delta V. So I get a final equation here of delta x equals V initial t plus 1/2. Now notice, it becomes t times acceleration times time, which if we were to simplify that out, time times acceleration times time would end up just being a and then t squared. This is kinematic equation number 3, and it's probably the most important kinematic equation out of all 3. Write this down, then advance to the next screen to see a problem. Alright, here are 2 problems that I would like you to do using kinematic equation number 3. Pause the video, then hit play to reveal the answers. Alright, in this last one right here, you'll notice that the problem has already been solved out. Notice that it has the equation written in both of them, the kinematic equation number 3. Now let's focus on the first one. The first one, the delta x, would be 52 meters. Now notice that the initial velocity is 0 because it started from rest. When the object starts from rest using this equation, you'll notice that this term goes away completely, since anything times 0 must be 0. So that leaves 52 equals 1/2 a 10.5 squared. A big mistake students make is they forget to square the time. Now, using your algebra skills, go ahead and isolate a, and your answer should be approximately 0.943 meters per second squared. In the second problem, notice now that you don't start from initial velocity of 0, but now you start with an initial velocity of 2.5 meters per second. So you'll notice that the equation looks very similar. It's 52 meters equals, but now we have to plug in the v initial t term. We have to plug in 2.5 as the initial velocity, times the time of 10.5 seconds, plus 1/2, a is what we're solving for, and 10.5 again, but squared. Make sure you do your algebra manipulation correctly on this one, and if you do, your answer should be 0.467 meters per second squared. So, in summary, these are the 3 equations that we went over. Notice that you'll use the first one, which is kinematic equation number 3. They're a little bit out of order, but it's going to be okay. You'll use the first one if you are given position and time. For the second one, you'll use that one if you're just given time. And the third one you'll use if you're just given position. This concludes the video on kinematic equations.